Hello and welcome to Basin Academy monthly safety trainings. This is your safety instructor, Jonathan Grinder. This month we're going to be covering hydrogen sulfide awareness training and respiratory protection safety. We're going to be covering basic fundamentals on how to keep yourself safe when encountering H2S or SO2 in the field. So with that, let's get this safety started. Okay, today we're going to be covering a lot of different objectives within H2S and respiratory protection. We have 8 course objectives. First, we're going to be covering introduction of H2S just generally. Where does it come from? How does it form? What is it considered? What's its elemental makeup? Yes, very exciting stuff. Then we're going to be talking about H2S as a chemical, H2S exposure, how it physically affects the human body, engineering controls or ways to protect yourself from H2S. We're going to be talking about contingency plans kind of at a basic level. They go extremely in-depth. There's all kinds of regulations regarding contingency plans, but we're just going to kind of stick to the intro level of those. Then we're going to talk about different methods that are used to eliminate H2S, what PPE we need or personal protective equipment will protect you from H2S. However, this is the last line of defense, just as a reminder. We'll go over that many times, but just, to hit that right away. And lastly, we're going to be covering respiratory protection and fit testing. So introducing hydrogen sulfide is pretty easy. It's found everywhere. Trace amounts are in pretty much all organics, including plants, who uses it during photosynthesis. It returns sulfur to its natural form during that process. It's also generally created when positive atoms of hydrogen touch the negative structure of sulfur. They have to make contact, and once they connect, you can get an H2S. They bond quickly and naturally. It's also used by humans as well as animals to protect the stomach lining from harmful acids. It bonds with sulfur underground in the earth and is present in basically in all crude oil. It's found in the air, and even in urban areas, it's very common in the part per billion, which we don't really measure in typically when we're talking about human safety, but it is there. But when high concentrations are absorbed by the atmospheres, it transforms into sulfuric acid, which is H2SO4, also known as battery acid. So it's very, very present. It's also used in human beings for nail growth, or sulfur is anyway, rather, as well as the, hair follicles in our body. Sulfur is everywhere, hydrogen's everywhere. So when those two come together, you can, again, kind of get the picture. It's everywhere. Common hydrogen sulfide synonyms, and there's quite a few names out there that people reference hydrogen sulfide as. It depends on what career, industry you're in. It also goes by sour gas, very common in oil and gas. Rotten egg gas, more, kind of common. Sulfane, sewer gas, swamp gas, sulfuretted hydrogen or sulfurated hydrogen, hydrosulfuric acid, and, as we know, H2S. In Espanol, disulfur hidride, sulfur o de hidrógeno, gas venenoso en hidrógeno sulfato. So those are your Spanish synonyms, just for those of you who are Spanish as a first language. Natural sources of H2S, again, it's everywhere, so it's in a lot of places. It can be in swamps, it can be anywhere where you have water that is stagnant, when you have time and opportunity for hydrogen to bond with sulfur without a lot of oxygen, and that's a key factor in the bonding, is just there's not a lot of oxygen. So underground, where we typically find hydrogen sulfide, you're going to see less oxygen in those environments. Typically super salty brines as well that have less oxygen in them, you're going to have more H2S. So that's why it's a natural gas in crude oil, in mines, in shafts, anywhere underground where you have the opportunity for hydrogen, which can come from water, or a lot of people think light, when it kind of ends its life cycle, turns into hydrogen. Hydrogen is everywhere. And the possibility for sulfur, either organic, typically it's an organic that turns inorganic through the bonding with hydrogen, you're going to get H2S. So again, I don't want to go too deep in the science. I bore myself a little bit with that stuff, so we'll just keep moving on. So industrial, it is an industry. We create it from time to time, depending on what different processes we're doing, but it's extracted in new material, raw materials. Sometimes it's a byproduct, such as paper plants will produce H2S, even sometimes sugar plants and plants that process a lot of root type vegetables will have some H2S or a lot of sulfur, SO2. So that's where we're going to see it in industry. Some industries that are affected, agriculture, as I mentioned, manufacturing and waste, we see it there, wastewater treatment plants, etc., sewage and treatment plants, landfills, excavation and trenching, depending on where we're excavating or trenching, petroleum and gas industry in all three streams, up, mid, and downstream, and really any industry where you're dealing with hydrogen, very common, and sulfur, very common, it's possible to see hydrogen sulfide. So it's classified as an inorganic sulfide. In its physical state, H2S is toxic. It's colorless. It has an odor similar to rotten eggs at very low concentrations, only at low concentrations, and it is highly flammable. It's measured in parts per million typically. However, as we get larger in concentrations, we're going to see it being measured in percentages. It's also measured in grains and pounds, and H2S isn't the only chemical or toxin that's measured this way. All chemicals and toxins can be measured this way. The energy industry, again, we typically measure in parts per million and percentage. In liquids, a lot of times you're going to see more pounds used when it's actually in the liquid itself. So visualizing what 1 part per million looks like in a million parts per million. All right, so I have this little diagram here. Essentially, you see the one drop, right? Let's think of a little dropper. You know, you're pulling it out of something, you drop that on the table or in a dish, right? It's barely visible. It's just not. So 1 drop of milk, let's say, for example, versus 14 gallons. So I just want you to imagine 14 people lining up and doing the gallon challenge. Just everyone trying to drink an entire gallon of milk and see how messy that's going to get. That's a lot of fluid compared to 1 drop. So when we're talking 10 parts per million, which is kind of the range at which your alarms are going to start going off, your personal alarms and fixed alarms, 10 is not that many compared to 14 gallons. So, and where we can smell it is if you take that drop, right, and you multiply it, or divide it 1,000 times in that part per billion range, that's when we can smell it, is in the part per billion range. So, a lot of people are like, oh, it's only, you can smell it. It's like, I need you to think about 14 gallons divided up 1,000,000 times, right, to these little drops, right? And then take that little drop and divide it another 1,000 times. And then some function of that 1,000 is when people are going to be able to starting to smell it. After so many, we can't smell it anymore. So I just really want us to wrap our mind around how small atomically 1 part per million is in the air. So some physical and chemical properties, going through those. It is combustible. As it burns, it produces SO2, which is also heavier than air, but slightly less, dense as H2S. Auto ignition temperature, it's very low, 500 degrees Fahrenheit, meaning if it reaches 500 degrees, it just automatically burns, right? That's pretty impressive. Flash point, minus 76.4 degrees. That's correct. So your typical day in North Dakota in the winter, H2S would be able to ignite if it hit that 500 degrees Fahrenheit. Melting point, not really something we're dealing with, but it is also very low. Flammable concentration, this is important, 4.3%, which is where most, gases, propane, butane, pentane ignite, is right around 4.3%. But most of them become too rich to burn at about 14%, and the H2S flies by them to 46%. It's still flammable, 3 times higher concentration than other normal gases. Vapor density, again, how dense it is, it's about 20% heavier than air, or more dense than air. So that's that 0.19. I'll give you 0.19, 0.20, whatever. Some people say 0.18. All we need to know is it's heavier than air, right? It's quite a bit heavier than air. Solubility, how it dissolves. It does dissolve very easily in water and oil, but as the temperature increases, it starts to come out, or it resolves into itself as the solubility decreases. So higher temperature, H2S will be released as a form of a gas. And again, we can see that by our temperature ranges there. It's very active even at low temperatures. So again, visualizing that flammability, it's extremely flammable. So below 4.6%, which again is 46,000 parts per million. So we're talking well beyond the level of fatal for the human being. But just even if we're working in that atmosphere under air or with the proper equipment or even with, some elimination techniques, if we're in that area, 4.6% toxic, but that's where it starts to burn. But again, and then before that, it's what we consider too lean to burn. And above 46% is where it becomes too rich to burn, or there's not enough oxygen in the air mixing with that H2S to ignite. However, I want you to picture, for this portion here, a campfire, okay? Campfire's burning, crackling, you're around it with your friends, roasting some marshmallows, telling the tales, maybe you got a can and a koozie, whatever you're doing, right? So imagine that smoke and how it kind of moves and shifts, and it'll, go, if it's me, it's always coming towards me no matter where I go. But depending on where you are in that fire, you're going to be maybe lightly getting the hint of smoke or just being blasted by the smoke, depending on where you're at. So the problem with this range here being trusted is, just like a campfire, concentrations of gas move very similarly through the air in clouds and whiffs and in wispy, ways. It moves very good. So if in one area you may be extremely highly, unless you're enclosed, right? In one area you may be in a highly concentrated area, and then the wind direction shifts, or because it's heavier than air, it changes its own cloud formation by its own vapor density. It can be another concentration somewhere else quickly. So, it's important to note, but it's also important to note that the, distance that we are from this stuff can make us safe or not make us safe, depending on where we're at. So we want to make sure we're upwind, crosswind, because those concentrations can change. You may be at 8 parts per million 1 second and 200 parts per million the next, just in a snap of a finger. So it is reactive with bleach, hydrogen peroxide, and certain acids, specifically hydrochloric acid. So again, that's where we have chlorine and hydrogen. And when you think of saltwater disposal, it's a lot of, salt water, right? And salt water and hydrogen mixing together with certain acids. It's going to bond together and either release H2S or even potentially form H2S. So during acid jobs on saltwater disposals, another place you want to be extremely careful. So this will cause fires and explosions. It's reactive with metal as well. So as I mentioned, casing, tubing flushes, acid jobs, etc. This can, have H2S come out of the formation or come out of the piping or tubing if it's kind of in contact with the scale. So it does transform. When exposed to oxygen, it can become H2SO4, again, sulfuric acid or battery acid. This also happens on volcanoes, or when volcanic eruptions occur, you're going to have sulfur, typically a lot of sulfur in the air, mixing with hydrogen that's in the air and oxygen that's in the air. It's going to bond together in a cloud, and then rain, and you're going to get essentially H2SO4 acid rain coming down. So just kind of keep that in mind. That's H2S again. When burned, it creates SO2. Again, that's where you get that in the atmosphere. And we're going to learn more about that here in part 3. When it comes into contact with iron, it forms iron sulfide over time. So what will happen is iron and other harder metals, they have a large porosity in the metal. So the hydrogen, meaning they have a higher hydrogen content, and the hydrogen from the H2S bonds with the hydrogen from the iron, and it kind of cancels itself out. Then you have the sulfur left, which will bond with the iron, the Fe that's in the metal, and it kind of creates something that looks like a scale or a rust. And that itself can auto combust, auto ignite when it's exposed to O2. So, when it's in old flow lines or abandoned pipelines, we're digging those things up. If we don't wet that pipe or fill it with water and cap it, preventing oxygen from entering it can catch fire. So that's something else to kind of note about H2S. Yeah, it's an intense gas. H2S is it's quite an impressive chemical, just by and large. I don't want to call it the ninja gas, but it is kind of the ninja gas. Finds every little nook and cranny, and has 100 different ways to kill you. So again, I kind of mentioned this on the last slide, how hydrogen bonds with harder metals. So a lot of times tanks will be lined that we know there's going to be H2S. They'll use different metals that aren't as porous, so that H2S can't bond with the metal. There's a lot of different tactics we can use when we know we have H2S. The problem is, in our industry, Wells have a tendency to become sour over time. So they may not be sour or over, essentially 8 parts per million in the stream for a long time, and then all of a sudden, boom, it'll happen either through communication with other zones during a frac. It can, kind of break up the zone and move an H2S area into another well. Improper treatment, if we're putting water down hole where organic material will break down and then, release sulfur, and then the hydrogen that's in the water and oil and the sulfur from the organic material that's breaking down will bond and create H2S. So untreated waters, a lot of different things can turn a non-sour well into a sour well. So H2S health effects, it does have an irritant effect on the eyes, nose, and mouth. Anywhere where there's, again, liquids or fluids, it's an acid, right? So H2S is an acidic gas to an extent. So imagine any sort of acid on your eyes, nose, mouth, tongue, lungs. It's going to be bad. Now, when that acid is in vapor form and you breathe it in, I mean, think Teenage Mutant Ninja Turtles, really anything. You breathe in that. I don't know why that came to mind, but you're breathing vapors in that are acidic. It's going to cause problems. Mustard gas, for example, Agent Orange, these sorts of vaporized acidic materials are going to have some pretty damaging effects. So, yeah, we want to make sure that we don't use our sense of smell to detect H2S for 2 reasons. One, it's only going to work in the parts per billion, maybe lower parts per million. After that, we need our sensors to detect for them. In addition to the negative effect it will have on the olfactory or the nose system, as well as the central nervous system. Because the body has H2S in it, the body doesn't necessarily recognize it as foreign. Maybe a little bit strange, but you walk into a cloud of peroxide, you're like, whoa, dude, vinegar, oh man, it's going to stop you dead in your tracks because your body's like, this is foreign. H2S is in the body. So individual susceptibility is another factor here. Different people are affected differently at various concentrations. So Billy may be at 8 parts per million really affected, and you're just hanging out, having a nice day. Whereas another person can be, sick at 12 and another person barely notice it. Over time, though, you don't build up a tolerance. Again, it's an acid, so it slowly breaks down your systems and makes them, more harmful. So just a little fact out there, 10 parts per million is the industry permissible exposure limit, meaning you can be around 10 parts per million for 8 hours a day. But they've done studies about people who've been around 10 parts per million for 8 hours a day for 30 years, let's say, right? And these are people that work in the smelting, typically, or, some sort of mining or metal processing, right? Guys that have worked around that. They're within the range, but over 30 years. And the statistics, as you can probably imagine, are not great. People get sick. People get really sick. A lot of different health issues. So even though 10 parts per million is probably not going to affect you, boom, right now, it's going to be more of a chronic effect than an acute effect. It can have a lot of chronic effects, and that's what research and studies are showing us right now. So how does H2S affect you in a more acute sense or immediate sense? So if you're experiencing lower concentrations, so really anywhere from 5 to 50 parts per million, you're going to experience dizziness, confusion. You're going to experience some form of headaches, eye irritation of the respiratory tract, euphoria and excitement even, sensitivity to light, diarrhea, and stare and gait. Once you hit those higher concentrations, so 50 plus, 200, 500, 800, basically anything less than what would be considered fatal, you're going to be experiencing pulmonary edema, where your lungs fill with fluid. It's also known as chemical pneumonia. Brain damage, coma is a possibility, respiratory tract damage and respiratory arrest, cardiac arrest. Your body, at these higher concentrations, it's let this toxin in, and it's trying to protect itself. So the lungs are going to fill with fluid because it notices something as foreign and causing harm to the lung tissue. So it's going to start sending fluid. The problem is the fluid isn't going to fix the problem like it would with, let's say, like an irritant like dust, where it sends fluid, it breaks it up, and then you can, get rid of it. It's just going to keep sending fluid and filling your lungs with fluid. But the problem is you need air because the H2S is actually going to replace oxygen in the bloodstream and then go to all these different organs, which your body's starting to shut down to protect those organs. You're not getting enough air because your lungs are filled with fluid, and it's just kind of a really downhill impact at that time. And again, this is an airborne toxin. It's an airborne acid. So when it gets into the bloodstream and the nervous system, and really anything that has a minor, a very small footprint in your body, it's going to attack those things. And if it can break down steel over time, what can it do to the small parts of your body in a very quick period of time? So chronic exposure, that long term, I got the sand here as a picture. Just imagine, the cumulative effect that sand inside of the lungs, especially a sharp sand, it's going to just slowly, damage more and more and more. H2S is similar, but again, it's more of an acid form. And just like the sands of time, the longer that it has the ability to impact you, the more effect it's going to have. So chronic exposure, a little bit different, some of the same symptoms, but you're going to see a few different things. You're going to see sleep disturbances, such as insomnia. You're going to experience nausea and vomiting, weight loss. You're going to experience fatigue, slowed pulse, digestive disturbances, corneal abrasions, again, cold sweats at nighttime. I mean, your body only has so many ways of telling you that something's in there affecting it. And, these are, very similar to things like the flu, the serious flu, right? Your body's essentially fighting back and doing everything it can to fight. So your body's going to experience a lot of sickness, and it's no different with H2S. So concentrations, again, we talked about the different ranges, from 0 to 50 to 100 parts per million. This is what we're typically going to see. Remember, 10 parts per million is where essentially under 10, they say, hey, you're good for 8 hours a day. But as we can see here from the symptoms that, nausea, tearing of the eyes, headaches, or loss of sleep from prolonged exposure, et cetera, from 2 to 5 parts, right? So even though OSHA says 10 is okay, we may want to, and you can, turn our monitors down to start telling us at 5 parts. Now, at 100 parts per million, that's what we consider the IDLH, or the immediately dangerous to life and health. And I'll get into that in a little bit, but that's where we're going to start to see some more permanent damage from the exposures at those part per million, or those concentrations. So above 100 now, it's just, between 100 and 1,000, depending on who you are, it's going to affect you differently, but that's where we start to see unconsciousness, the lungs starting to fill with fluid. And at 1,000 parts per million, we call that the DRT, which is not an OSHA acronym. It stands for dead right there. So keep that in mind. DRT, not a real thing, but 1,000 parts is pretty much where it's game over for everybody, which is still, again, 0.1% part per million. So very, very small. So the byproduct of H2S, I already mentioned this, is SO2. It's 2 parts oxygen, 1 part sulfur. Sulfur is very heavy, just like, it is in the H2S. If you see the bigger atom, which is the blue atom, and the H2S and the blue atom here, sulfur, it's recognized as larger because it's heavier. It has a heavier density. It's 32 to hydrogen that is 1. So the SO2 is created when the hydrogen's burned off and it's introduced to oxygen. And for something to burn, it has to have oxygen as a part of that mixture. So that the sulfur leaves the hydrogen and then bonds to the oxygen. You get SO2. Benefits of SO2, a little bit less heavy than H2S, still heavier than air. The flammability is gone, so now we're dealing with just a toxin instead of a toxin and an accelerant. So that's another benefit. And then thirdly, you can detect SO2 even at higher concentrations because of the burning that it burns your nose, much like a match would, after it's been put out. We're smelling a little bit of SO2 there. So chemical and physical properties of SO2. It is also classified as inorganic sulfide. It's also highly toxic. It's colorless, but it does have an odor similar to burning matches, and it is an irritant to the olfactory system, as I kind of mentioned before. As an element, it is, again, very similar. It has additional names: sulfur oxide, anhydride, and sulfurous oxide. Again, it's heavier than air and will collect in confined spaces and low-lying areas, so keep that in mind. So its chemical and physical properties, its vapor density is 2.26. Its flammable limits, again, it's not flammable, so that's good to know. It does have a boiling point and a freezing point, which is a little bit different than H2S. Again, since we're not dealing with an accelerant, it is a little bit more impacted by cold temperatures. So it does have some reactivities, not things we're typically working with, but ammonia, zinc, brass, copper, aluminum, and water. So SO2 exposure compared to H2S exposure, again, your body only has so many ways of telling you something's wrong, so it's going to be similar. You're going to experience suffocation, irritation of the lungs, irritation in the nose, throat, and mouth, dizziness, headaches, nausea, vomiting. All these things are going to be another, way that your body tells you, hey, I have a foreign contaminant in me, and it's not good, so I'm letting you know. So again, from 1 to 100 parts per million is kind of our danger zone. Above 100 parts per million, that's where we're really going to start experiencing those higher issues, those acute sicknesses. And then over 100 parts, which is the ideal H for SO2 as well, that's where we're going to see permanent damage being caused by it. And then it's just kind of a crapshoot, your personal exposure, susceptibilities, et cetera. But again, just like H2S, although, SO2 is a little different. Between 500 and 1,000, somebody can be instantly dead or DRT. Just, again, depends on the person. So accepted exposure limits, as we mentioned, with OSHA, it's 10 for H2S for 8 hours. The ACGIH, however, in the API action is also 10. The ACGIH is 2, but the API action is 10 for SO2. It's 2 parts per million, which again is the permissible exposure limit. So I think they know something that OSHA hasn't codified yet. Routes of exposure for both gases. Inhalation is the most common, by breathing it in because it is in the air or mixed with the air to some degree. Skin absorption can happen if it's in liquid typically. If you're a water hauler or an oil buyer or somebody who's roustabout, someone who's cleaning tanks, things like that, it's possible to get it on your skin. Also, same, kind of method, ingestion if it gets on your clothes and then onto your skin and into your mouth. Injection, not as common, but that is a chemical exposure. If you're using a pressure washer and, somehow the grease and oil that has SO2 in it gets punctured into your skin, it could happen, or on a sharp object or something, but that is a little bit less common. Ideal H. So I mentioned this before. Ideal H, it's not an arbitrary number, but it's a number along a range of a toxin from 0 to 100%, right? Where exposure at that level will cause permanent, irreversible damage to some extent to your body. Whether it's, it damages a little bit of tissue, it burns out, some nerve endings in your nose, or in your, scars to your lungs a little bit. Like there's permanent, irreversible damage at the ideal H level. And so at that level, that's where a respirator is required, like a full face piece respirator with supplied air so that you're not breathing it in, right? That it's not impacting your lungs, etc. And that's for any toxin. In H2S, that's 100 parts, and SO2, it's 100 parts. But again, what we're seeing is that SO2 is known industry-wide to affect you at half the levels of H2S, but the record books, the OSHA rules kind of put it in the same category, but keep that in mind. Ideal H atmospheres, some other things, we have to consider is even if we don't know the levels, we're automatically considering that the level to be ideal H. So for example, base and safety on the service side, not the academy side, but we send guys to do H2S testing as a part of their kind of daily job function. And for them, if we get a call and they say, hey, we need you to go to this well, we think it may have H2S, we don't know. Can you go test it for us? So if we know a well is at low concentrations, right, we may be able to test that by ourselves if it's under 10. But if it's over 100, or rather if we don't know, or if it's over 100, we treat that well the same. So we'll send 2 guys. They're both fully masked up. They're both under air. One might have an air line. One might just have a 30-minute pack. We got a buddy system. We got a rope out. I mean, we're like ready to rescue a guy in case something were to happen, right? We treat unknown wells or unknown situations as though they were fatal because you don't know. It's nice to be optimistic, and I'm kind of an optimistic guy, but when it comes to H2S, there is no room for optimism. It's all bad all the time. However, and we're going to get into this in a little bit, there is a way to prevent exposure, and we do it every day. This is part of our work scope, so there is a way to prevent exposure and potential, harm to your body. So for both SO2 and H2S, again, the IDLH is 100 parts per million, so keep that in mind. So as I mentioned, there are some ways to prevent bodily harm from H2S. And this is kind of a tried and true method for any hazard, including we'll apply it to H2S today, but it's called the hierarchy of controls, where we say, okay, the best thing we can do is eliminate it completely. All right. How do we get rid of the H2S totally, right? Can we vent a tank completely? Can we chemically treat this well? Can we shut the well in, plug and abandon this thing? It's high H2S, which a lot of times they do at certain levels. That's an elimination tactic, right? Most effective, not always possible. Substitution, not really feasible with H2S. Some people may call chemical treatment a form of substitution, and I can get behind that. It's a little bit different, but where we actually chemically treat it with, typically it's called an H2S scavenger. And what these H2S scavengers do is they attach themselves to the sulfur atoms and then drop it out because it's heavier than hydrogen. The hydrogen will, escape vertically or go to the top, and then the sulfur will drop horizontally or go to the bottom. That's also in the engineering control phase. So the chemical treatment is kind of a blend of three, right? Because we're eliminating it by substituting a new chemical, which is an engineering control or something that we add to the process to prevent the hazard from impacting us. So other engineering controls would be venting, flaring, vapor recovery systems would all be considered engineering controls. Then administrative controls and PPE, those are at the bottom here. Those are the least effective methods of protection. Those are things like signs, SDS sheets, labels, PPE, get into that. We'll talk about that more in depth here in a minute. It's what we wear physically to protect ourselves, but we want to do the top three if we can, right? We want to plug that well if we can. No, just kidding. For any oil and gas people, I'm just joking. But sometimes, if it costs more to treat the well with chemical than the well makes in productive oil or gas, it may make sense to plug and abandon the well because it's no longer economically feasible. And are we talking about economics here? Yes, because the safest thing to do is never go to the field, or if there's H2S, just never go to that site. Some companies have that policy. For us, we found that through chemical treatment, through different safe work practices, where you stand, how you stand, where you direct the flow, do we vent, flare, different pressurized systems, different tools you can use subsurface. There are different ways to protect yourself. So that's kind of where I lean and the industry leans, and those are the best ways to protect yourself. PPE being the least effective method of protecting yourself. So again, flaring that's one great engineering control, where essentially we take any excess gas and then we send it to the flare, right? That typically goes through the treater, and then the excess gas is sent to the flare. Depending on the system, this may be more or less effective. If it's designed really well, it's very effective because you can even send the tank vapors to the flare, which Continental's done successfully in a lot of their wells and others. So just keep that in mind. At that point, SO2 is the greatest concern. So those flare stacks being higher is better, right? Because both SO2 and H2S, when they come in contact with wind, there is a high dispersion rate. So when wind hits it, boom, it goes from high percentages to very low part per million quickly. But what do you do when there's no wind? Because it's 2 times heavier than air, or 1.18 times heavier than air. With no wind, that's where we start to see issues. So some administrative controls, JSAs, windsocks are administrative controls, signage, training is an administrative control, safe work practices, lockout, tagout, equipment inspections, rotating workers so they're not, wearing a mask for 14 hours a day, things like that would all be in the administrative controls, things that we can do logically to alert people of the danger and then also prevent them from being exposed longer than they should. So safe work practices, these are extremely important. Like, I don't think a lot of people take into consideration how important these tools are, but planning the work, thinking through everything that can go wrong, even if it's like very low likelihood, like start at the worst case scenarios and then work your way towards what you're about to do, and then figure out ways to prevent those things from happening. Barriers, ventilation, fans. I mean, there's a lot of different stuff. Well, what if this happens? Well, let's get a fan out here so it disperses it quickly. Whatever you have to do. And then as well as inspecting your equipment, making sure people are standing upwind at all times, no matter what, even if they are under air, make sure they're standing upwind, like prevent the exposure as best as you can all the time. So safe work practices, again, communicating with people, having a buddy out there. These would all be safe work practices. Like, hey, I'm going to drive into this area where we know has H2S. If I don't call you in 15 minutes, send somebody. There's gas monitors that if you fall over on your side and are inactive for so long, it'll send out a signal and people will come for you. Like, there's a lot of unique administrative controls out there. But again, these are good planning tools. The best thing we can do is get rid of it completely. If not, then we need to make sure we have very strong administrative controls in place. So the important moving crosswind, upwind. So let's say we have a pumping unit out there, and at the pumping unit somewhere, might be the flow line, might be the casing valve, we don't know, right? There is an H2S release, okay? So it's growing towards us. It's really starting to come out and kind of come towards us. Our monitor starts going off, then it really starts going crazy. We're going to want to go crosswind first, and then we're going to want to go upwind to the muster point. And the reason we want to go crosswind first is if that individual would have went straight upwind, we always say upwind, crosswind, right? But really, it should be crosswind, upwind, because if that individual would have went straight upwind, he went right towards the source, right? So crosswind either way, and he could have went, in this case, north or south would have been crosswind. But either way, go one crosswind direction before you start going upwind, where you know that you're safe from the source. So contingency plans, and I said we go into this in brief, so I'm going to make this brief. Contingency plan deals with two things. One, how to protect the public that are in the area and the people that are working on site, and secondly, what the actual processes are for stopping the release or preventing the exposure from growing, right? So it's actual physical tasks and steps to take. So it's not like, be careful, go upwind. That's good. That should be in your JSA every single day. So that's, part of a contingency plan, certainly. But, that goes into much more detail of what we do if there's an H2S release. This becomes extremely important in drilling operations. That's where we see it most commonly, but it can also be in any sort of emergency event. Then, contingency plan, emergency action plan kind of go hand in hand. There's also a lot of regulations involved with proper contingency plans and emergency action plans for specifically an H2S release. Because it is so toxic. So immediate action plan, this is something that we should have in place if and when an H2S release happens. So this is for everybody all the time. So the first thing you want to do is stop breathing. That's easy to say. I don't know if you've ever tried to stop breathing and then start running. It's difficult to get very far before you have to take another breath. So keep that in mind. We want to purge and don our escape packs. We're going to talk about different escape packs in a bit. Make sure that we understand wind direction. And, my advice to you is always kind of be aware of the wind direction on site, wherever you are. Like, I'm upwind, I'm crosswind, I'm downwind of the wellhead, of the treater, of the tanks, wherever you are all the time. And then you want to move crosswind and then upwind, as we kind of already talked about. Next step is to alert affected personnel. Make sure everybody knows that there's some release once you're safe and protected from it. You don't want to let people know as you're getting gassed and you go out. That's not a good situation. Go to the briefing area or the muster point. Account for everyone that's on site. If you're trained to do so, you can go rescue people and have the equipment, but you need to have approval to do that. And some companies grant approval prior. If this were to happen and you're trained, you can go in there. And other companies have you must get approval before you go and enter and help somebody. So if it does get exposed, then through inhalation, then we have to assess what the priorities are. And the first thing you want to do is protect yourself, right? You want to call 911. If you have two people there, the other person should call 911. If you're the only person there with the person that needs to get rescued, that needs to be your first call before you go help them. You want to protect yourself, meaning you have to have the right respirator on, the right rescue equipment on. You need to be able to rescue them effectively, because if you go down while rescuing them, that creates two people that need to be rescued in the future instead of just the one. Once you get them to fresh air through your rescue techniques, you want to make sure you keep them warm and at rest. And if the person has stopped breathing, you want to give them CPR avoid mouth-to-mouth in these situations because H2S may be in the air that's in their lungs and you may be exposed that way as well. So if it gets in the skin or the eyes, just like most chemicals, we want to rinse them out for 15 minutes, rinse it off the skin, rinse it out of your eyes. Again, corneal blistering can happen. So we want to make sure we get those eyes cleared out as soon as possible. There's some discussions out there about contact lenses, and a lot of people say you cannot wear contact lenses. I can disagree with that, but at this level of corneal blistering and stuff, like, it's an acid gas and it's going to cause a lot of problems one way or the other. It's not minor indifference, but minor enough. Facility surveys. Okay, so moving outside of the first aid side, companies are required to test their wells for H2S and then communicate that information to contractors. They don't have a crystal ball, though, so they don't always know what future wells will become sour over time. And it does happen, as I mentioned before, through communication with other zones, etc., fracking, different things can create a well to be H2S over time. So, they should be testing these wells at least every year, every 3 years, depending on their plan, and then communicating that to subcontractors. Anything over 10 parts should have a breathing air system on there. If you see a sign that says danger or warning, H2S may be present, that's essentially true because H2S can be everywhere. Some companies like to put these on every well, all right? So keep that in mind. But then once you see a breathing air system or a windsock that's red and white, then typically we know that there's H2S, and when there's a red and white windsock, it's over 100 parts. Not every company does that, but if you see that, then that's what that means. There's different gas detection equipment out there that we use for surveying facilities. Some of them are permanent, some of them are mobile, some of them are just remote area monitoring, and they're used in different instances for different reasons, but they do need to be calibrated and maintained properly. They should be bump tested and inspected before use each day. We don't want again, you can adjust the alarm. So we want to adjust that alarm, if anything, to be lower than 10, not above 10. It's got to be at least 10. Make sure you know how to use that monitor before you put it out in the field or wear it. Like, someone just hands you a monitor and says, wear this. Like, no, you should probably, how does it work? What does it do when it sounds? Ask some questions, read the manual, be familiar with that monitor. So personal monitors, typically we're going to see 4 gases out there. Sometimes you'll have single gases. Typically, if it is a single gas, it'll be H2S. But you could have a single gas for any gas, SO2, methane, propane, benzene. You can have personal gas monitors for almost anything. But typically we see the 4 gas monitor out there instead of just the single gas. They typically measure for LEL, carbon monoxide, H2S, and oxygen. So looking at them, essentially what happens is the gas passes over the sensors and it's constantly reading. It's designed to be in your breathing zone so that it's reading the air that you're breathing. And then when it alerts you, it's not just saying, hey, there's H2S around. No, or LEL. There's H2S or LEL exactly in the air that you're breathing. So hey, this is something I should be really paying attention to. And that breathing zone is identified in RP 49 3.2.3. Not going to ask anyone to remember that, but it's a chart, and it's about 6 to 8 inches from the nose and mouth, basically in a circumference, up, down, left, right. That's where you want to have your monitor. Personal monitors must be worn essentially by everyone out here that are at risk of H2S, exposure. Which again, it's in every well. It's on every well site. It's in every ounce of crude oil. The question is, in every CFM of gas. The question is not is H2S present. The question is how much H2S is present. And that's really the main function here. So anyone who's exposed over the PEL should be monitored kind of on an annual basis, making sure that they're not getting sick over time. So fixed detectors, on the previous slide, I had a little circle on the bottom of where that yellow monitor is. You can see that little kind of oblong obelisk there coming down. That is the sensor. So again, just like your personal monitor, this is kind of protruding out and it's fixed, meaning it's bolted there to that site. I took this photo and essentially at a gas plant, and they have about 40 of these around the location, and it's designed to tell us if H2S is present. There's also ones for LEL, letting us know if errant gas is floating around the site or facility. A lot of times these are set up to alarms and lights, so that if it detects gas, an alarm goes off, a light starts flashing, someone in a control room somewhere sees it and can kind of communicate through the plant that, hey, there's H2S in this area, wherever that monitor is. There's also remote monitors. These act like the fixed monitors. It's an exposed sensor. These can have pumps or not have pumps, but typically they're designed to measure a circumference area of about 100 feet to 300 feet maximum. You can move this thing around. You can pick it up. It's about 5 pounds. You can move it wherever you want. Hey, we're doing some pipeline blowdown work over here. Let's put it over here just to make sure it's not, going into Farmer John's field, killing his cattle, et cetera, et cetera. And you can hook these up. I think they have up to 7 gases you can put in there. Benzene, LEL, SO2, H2S, propane, whatever you want to test for, you can get those sensors put in here. So then you have 4 gas monitors with pumps. You can also do single gas monitors with pumps. I mean, again, there's a lot of configuration, but essentially they're also called direct reading measurement devices. So the end of that black, that hose there has that black tip, there's typically, it's going to draw air into this monitor and it's going to read it from, an area away from you. So you're not like right in it. Some guys use their personal gas monitors for this. It's not effective, doesn't work. The amount of time necessary to read, depending on how quickly you're moving that around, may or may not work. So the pump is designed, you put it out there, you wait a few seconds from wherever you're reading, and it's going to bring you back a reading of where your measurement device is and what the levels of concentrations of, again, H2S, SO2, CO, whatever gases it is you're measuring, that's their designed purpose. So again, they need to be bump tested every day. A bump test is going to tell you a couple things. Mostly it's going to tell you if the sensor is working, and it's going to show you that all the lights and alarms are working properly. So a bump test gas typically sets it off at 10, right? Hey, I'm going to feed this thing 10 parts per million. If it goes off, we know that it's designed, that it will go off at 10. And these monitors fail a lot, right? Leaving them out in the cold, dropping them, leaving them out in the heat. A lot of things can affect the sensor and change what it's reading, which is what we call calibration drift or sensor drift. And it's going to change from, maybe it starts reading at 12, right? Or 14 or 20 instead of 10, or maybe even less. Maybe it starts reading at 5 when it should be reading at 10. It can drift either way, but that's why a bump test is important. So calibrating them, typically 90 days is kind of the industry standard, but there are a lot of different brands out there. In fact, I've shown you pictures of about 4 or 5 different ones already. Typically 90 days is the standard, and this is looking not just at the low level alarm, does it trip when it's supposed to, but also does it read accurately up to its high level. And so calibration takes it through the whole gamut, and if it's a multi-sensor, it'll take it through every single sensor, make sure all the sensors are working properly. And that concludes our H2S portion for today. This is what we call H2S Awareness Pro, so keep that in mind. This is a Basin Academy exclusive training. Now we're going to move into respiratory protection, which is a 1910-134. Very basic, things we need to know about respiratory protection if we have to use them. So medical surveillance is kind of the first tenet of respiratory protection. Basically, are you qualified to wear a respirator at all? And different things can prevent that from happening. Claustrophobia, lung disease, heart disease, any sort of issue where if you don't get the proper amount of oxygen, then you will pass out or get sick or have some long-term effect. The medical surveillance questionnaire and then review by a doctor is required so that we're ensuring that the people who are wearing respirators should be wearing respirators. Because if not, then maybe that's not the job for you. Maybe you should not be in a situation where you need to wear a respirator to be safe and survive. So if someone's exposed ever to H2S, kind of stay on the medical vein here, they do need to be followed up by a doctor. They can't just say, oh yeah, I'm fine. I was sick for a couple days, but I'm good now. No, you need to get checked out by a doctor because there may be lingering effects you're not aware of, and a doctor's going to be able to run tests and tell that. So PPE, as I mentioned, is the last line of defense. We know this. Again, 1910-134 is what deals with this. Essentially, the respiratory protection program requires employers to look at the chemical or atmospheric hazards someone will be exposed to and provide them with the training and equipment, et cetera, to protect themselves from those hazards. So other safety equipment may be required, FR, maybe gloves of certain types, that prevent absorption into the skin. But we're not going to get into those too in depth here. But we do want to make sure that none of whether it's oil or water or any kind of fluid that may be have H2S dissolved in it, that doesn't get on our skin or in our eyes. And so glasses, respirators, FR clothing, rain gear, etc. may be important depending on what type of work you're doing. So there are a couple different types of respirators that we look at in general. You have supplied air respirators, which is generally any respirator that's giving you a contained air supply, right? And sometimes these can even be being filtered as it's giving it to you. Those type are not approved for H2S, but they do exist. Then you have a particulate filtering respirator, and this is where you see, it's filtering out whatever, airs through the air whenever. We're very familiar with these now over the last few years, but this is the type of respirator that's going to filter it out for you. So supplied air respirators are the only type of respirators that are approved for H2S over 2 parts per million. So basically at any level that's matters to us at all. And so we need to have our own air supply that's being fed to us. There are different ways that exist for us to get that air. So we have an air-line respirator, which was in the photo we saw a moment ago, where an individual has an auxiliary pack or a 5-minute pack hooked up to a line that's hooked up to a contained air cylinder that's feeding them air. We also have an emergency escape breathing apparatus, otherwise known as an EEBA. Typically has a bag and a valve, and that's it, and a container. So you pick up the container, you turn the valve, you put the bag over your head, you have clean air. These are good for situations where you don't have a lot of time, the concentrations are high, and or someone has a beard or a mustache. So SCBAs, there's 2 different types. There's your 5-minute or your SKA pack, also known as an escape pack. Says you get 5 minutes of air, but that can change, and we'll go into that here in a minute. And then you have a 30-minute pack. There's 45-minute packs, essentially, again, providing you with clean air to a full face piece respirator mask. So here's some pictures of those. So the EEBAs there on the left, there's a 5-minute and a 10-minute. The orange is 10, the yellow's 5. That little clear bag on the top actually goes over your head, and then there's a valve, and boom, you got clean air. The airline respirator and the rescue pack, those have the masks that attach to them, and then they have a regulator that clips into that mask. You need to purge it first, and you can take a little bit of time to put on. So keep that in mind as you're out there working. That those we say hold your breath and put on your respirator. These can take a little bit of time, so make sure you're practiced if that's a real hazard that you may be up against. And here at the bottom, I mentioned that it says 5 minutes and 30 minutes, but depending on the user, that could be 2 minutes. It could be 12 minutes instead of 30 minutes. So keep that in mind. It's a maximum air volume based on typical breathing air usage. The typical person uses about 100 CFM of air per minute. So 100 CFM, cubic feet per minute. That's typically what we're going to, drain it down. So keep that in mind. So employers are responsible to provide the respirators, as I mentioned, make sure their people are medically qualified, make sure that their people are fit tested, which we'll talk about here in a little bit. Also give them the PPE that they need and train them to the hazards, the respirator use, etc., as well as their monitors. So really a lot of the onus on this comes down to the employer. So if you don't feel adequately trained and they're like, here's an SCBA, ask for more training. Companies like Basin Safety, Basin Academy, we provide this training. We can come to facilities. You can get it online. For a lot of this, I highly recommend, and OSHA recommends, and the API recommends, and the ASME recommends, and I could go on, that you get hands-on experience and training instead of just learning from a video such as this. So written respirator program is another requirement for employers. Basically needs to outline when you need to wear a respirator, how many parts per million, which it needs to be at minimum 100. It may be less though, maybe 50. I don't know. Your program may say something different. It also talks about change out schedules for PPE. Does each individual get their own respirator? Do we share respirators? Like, what's the plan? This is all the things that are going to be discussed in your respiratory protection plan. And again, it must meet the requirements of 1910-134. So monitoring that program is also the company's job. So, however, the process in which this happens needs to come from the field, right? You can't just say, oh, the management should know about this problem without us telling them that it's a problem. That's not realistic. So if we're going to monitor these programs, which the companies are required to do, we need to give them feedback. If the respirators aren't fitting properly, or the cold is damaging them, or they're fogging up too bad, all these things need to be communicated so that the management team knows and can adjust to those needs. If you have to leave a work area where you're wearing your respirator, that's fine. No big deal. The mask is fogging up, you're getting sweaty, you got to itch your face, whatever. You can do those things, but you must go to the briefing area or the green work zone instead of the red work zone where the contaminant exists prior to doing that. Also, if you have to replace some part of it or it's not sealing properly, etc., you need to do that in a safe area. Cleaning the respirator, this is probably one of the easiest things to miss in the program because it does take a lot of, tedium to clean these things. But there is a hack, and I'm going to tell you the hack today just so we get it. Yes, you have to wipe it down. You should wipe it down before and after use with a non-alcoholic towelette. Absolutely, no questions asked. But just wiping down the face piece doesn't really get it fully clean. That's pretty good, on a day in, day out, but at least once a week, if you're using this thing a lot, you want to wash it more thoroughly. Bacteria can get in there, start growing, you get a colony, you put on the mask, you breathe it in, you get sick from your respirator. That's not a good situation. So a very easy hack here is to take your respirator mask, put it in some warm water, warm soapy water, just a little bit of Dawn dish soap, nothing crazy, no bleach, right? And then get some sanitizer tablets that they use for dishes. They're like dry pellets. They'll use them in restaurants. Very inexpensive. Get one of those. You can break off half if you're just doing one mask, or one whole if you're 2-3 gallons of water. You're cleaning 5 or 10 of these bad boys. After you wash it, let it soak for a little while. Get all that grime and bacteria up. Then you're going to dip it in the hand sanitizer, the dish sanitizer. Which is food safe, it's food grade, and it also helps with the bacteria, etc., and make sure that mask is nice and clean. So we want to use warm water, mild dish soap, a mild disinfectant. Again, that's why I like the sanitizer stuff. And then dry. If we're not going to air dry it, then dry it with a lint-free, something like a chamois that doesn't have lint on it. And the reason for that, and it has to be a lint-free chamois because there's different chamois out there. Because that lint will get in there, get wet, get bacteria on it. Bacteria will grow, make a colony, you'll breathe it in, and the respirator will make you sick. Sorry for doubling that up, but it's true. So we want to make sure we keep it dry and then free of any contaminant, including lint. So storage, same thing. Again, we don't want dust in there, dirt, grease, grime, etc. We want to make sure it's in a nice, dry, protected state because it's a life-saving device. We don't want it to be crushed underneath the seat in your truck. We want to make sure it's in a nice hard case so that it's protected at all times. Inspections should be done at least annually, as far as from a certified person, but prior to each use, we want to inspect it as well. If it's just sitting on the shelf, still should get checked out at least once a year. What they're going to be looking for is tightness of connections, tightness of fit, quality of rubber sealing, making sure that there's no rust on it, all the parts freely move, and that the expandable headgear tightens correctly. All those things are what they're going to be looking for. Voluntary respirator usage. So let's say you want to wear a mask at work, right? You just want to. It's your prerogative. You totally can. But you can't then pick and choose what part of the program you want to follow. You got to follow the whole program, the fit test program, the cleaning requirements, the change out requirements. All that needs to be followed if you choose to wear a mask where it's not necessarily required. So selection of respirator, again, this is on the company. NIOSH has, and I just took a screenshot here of some of their guidelines online. NIOSH has some different recommendations for selecting the proper respirator. And respirators, when they're made, have to follow ANSI standards, just like safety glasses and boots and FR. They have to follow a certain standard. Within that standard, though, depending on the contaminants you're working around, that will change what type of respirator that you use, not to mention the type of cartridge that you use. So you have to check the SDSs and then verify that with the marking on the respirator or the purchase documents of the respirator to make sure it's the right type for you. Makes it easy in oil and gas, specifically H2S. Scott, MSA, and 3M, as well as Draeger and a few others, have kind of the standard package that's, good for oil and gas, is resistant to grease and oil, and then will protect you from H2S, which is the full face piece breathing apparatus. So IDLH atmospheres, again, we need to have that full face piece pressure demand self-contained breathing apparatus, which is the full scope of it. Full face piece pressure demand supplied air respirator with auxiliary self-contained air supply, which is essentially a pack with a hose and a regulator on it. That's essentially what it's saying. So essentially, it also in areas where we don't know the concentrations, we consider that to be IDLH. Or if there's low oxygen, if it's below 19%, 19.1%, we consider that to be an IDLH atmosphere as well. So with respirators, they also have an assigned protection factor, also known as the APF. The APF is a number assigned to a respirator based on the amount of protection it's going to give you. Now, the respirator mask and face piece itself may have an APF, and then also the cartridges may have an APF. So we want to choose the highest APF possible that's feasible for the type of work that we're doing. Obviously, if you're giving yourself your own air supply, that's the highest APF possible, because we're not filtering anything out. We're not like, is this filter good enough for the contaminant? We have our own air, right? But if we're wearing a filter mask, then we have to make sure that APF meets kind of the demand of the chemical that we're working with, which is going to be given to us in the SDS. So the service life of respirators, it changes based on manufacturer, use, wear, tear. Was it dropped, kicked, booted across the yard? What do we do with this thing? All that's going to determine service life. So there's the minimum and the maximum, and that's going to be stamped typically on the respirator or with the purchase documents as well. Medical evaluations, I already mentioned these. The one thing I didn't mention is that they do have to be done whenever you first go to wear a respirator, and then typically if anything changes about your health afterwards. Not a bad year, minimum 5 years, but as we gain weight, lose weight, have any sort of medical condition change at all in our body, high blood pressure, low blood pressure, cancer, lung disease, heart disease, anything of that nature, we need to be re-medically evaluated. The reason for this is we just want to make sure that wearing the respirator isn't going to create another hazard, right? Our PPE can cause problems, but we want to make sure that it doesn't. Fit testing, however, does need to be done every single year. There's a couple different types of fit testing, but essentially what fit testing does is ensures that, one, the respirator fits your face shape, and secondly, that it's actually protecting you from contaminants that are coming outside of that mask. There are two types of fit tests. There's the qualitative. This is an example of the qualitative, and specifically with the bag over your head, this is for the half mask style. They're typically irritant smokes are used. They put it around the person. They have them do a series of exercises and talking and just normal work activity type movements. And then if you can sense the contaminant, then you don't have the proper fit or the mask isn't sealing properly, that's what we consider a qualitative. Then we have quantitative. A quantitative, this is going to measure a bunch more factors, like what's the sealing percentage, how long until the air diffuses. It's going to look at ambient air pressure and then negative air pressure inside and outside of the mask. So much better, fit test, uses a machine. It's, very accurate and particular versus the other one where we just kind of blow smoke around you and say, yep, you're good to go. Repeating fit test. Again, I mentioned annual. I also mentioned the needs for, redoing your medical qualification. Same thing with fit test. Gain a lot of weight, lose a lot of weight, some change to your face, dentures, you get surgery, etc. All these would be a need to repeat your fit test even more often than annually, but at the minimum every single year. So seal checks. Respirator seal checks are going to be done every time you go to put the respirator on. So you put it on. You want to make sure that you do a negative pressure test and a positive pressure test. To do a positive, you're going to place your hand over where the regulator would clip into, and you're going to breathe out. That's going to give a popping sensation. And you don't breathe out as hard as you can because you'll definitely break the seal, right? But a normal breath, and that should hold within that mask. And it's the same thing for a negative, except for you breathe in a normal breath, and it should pull in, and you should not hear or feel any air coming through the seal of that respirator mask. Importance of maintaining seals is obvious. If you don't, then the contaminant gets in. So the most common reason a seal will fail will be facial hair, or actually the hair on top of your head. That can block, if it gets in between your face and the seal, it will block the seal from sealing properly. And so we have to make sure that we're wearing here's kind of a picture of where the masks kind of settle on your face and why you need to have, the appropriate style of clean shavedness, I guess. So the green one on top is really the only right one. You can get away with a small mustache. You can get away with just the soul patch. You're going to look ridiculous, but darn it, if you want to look like Burt Reynolds, you just go right ahead. You'll be perfectly fine doing that. So standby personnel, I mentioned these in brief. This is the guy who's working outside of the red area or the red zone where there high levels of H2S exist. His job is to rescue if somebody were to go down. He's not to be on his phone or doing something else. His job is to be focused on the people working in the H2S area and be ready and equipped and trained to provide rescue if necessary. This may be done by means of a rope. This may be done by means of going in and grabbing them, a winch. There's many different ways to rescue, but this person, that's their job, is to essentially, be prepared to rescue in the event of an emergency. A buddy's kind of the same thing. A buddy may or may not be trained to rescue, however, so keep that in mind. The buddy's job may be only to call 911, which isn't a great scenario if you need to be rescued immediately. But that's what a buddy is. His job is to kind of pay attention to you, make sure that if something happens, that you get medical help or rescue quickly and confidently. So lastly, kind of wrapping this up and summarizing, I try to keep it under an hour. We're just over, but we want to make sure that we understand that H2S is colorless, it's highly toxic, it's also flammable and heavier than air. It's formed when decomposing material happens, or really any time a sulfur element bonds with two hydrogen elements, then you're going to get H2S. The action level for H2S is 10 parts per million, meaning that that's the point where we need to muster up if we don't have the appropriate PPE. IDLH for H2S and SO2 are 100 parts per million. Individuals that are exposed to H2S at any level above the PEL, which again is 10, need to be seen by a medical professional immediately. Respirator equipment, meaning full face piece respirator equipment and self-contained auxiliary breathing air supply, must be available and used by workers at over 100 parts per million, otherwise known as immediately dangerous to life and health, or IDLH. And the buddy system is also required in IDLH atmospheres at 100 parts per million or more. Mel, it's at the bottom of the quiz there. Let me know. There's always usually something somebody brings up. I love to hear your feedback, even if it's like, hey, Greiner, you need to work on your pronunciation, you're speaking too fast, whatever it is, I'm here to listen. I want to make sure this is the best possible and most excellent training. So with that, let's keep this safety going.